Okay, we're going to get started today by talking about cyber-informed engineering. And you're going to hear a lot of themes in our conversation that are going to resonate with things that you have been hearing throughout the conference. So we're going to start. Again, I'm Ginger Wright. I'm a portfolio manager at the Idaho National Laboratory, and I get to have a whole lot of fun with cybersecurity for critical infrastructure. Everything from being part of exercises on spooky disease islands to testing some of the most interesting equipment and looking for vulnerabilities and working with vendors to fix it. We get to do it all. So if you're interested in Idaho National Laboratory, please come and talk to me. Andrew?
Hi, everybody. Thanks for being here. So I work in the water and wastewater field exclusively at this point, and my firm, West Yost Associates, was the first CCE or consequence-driven cyber-informed engineering licensee from INL. That's how I've gotten to know Ginger and become a bit of an evangelist for the water sector to spread these ideas from cyber-informed engineering and CCE. We provide all sorts of services across the life cycle of control systems and IT systems to our water and wastewater utility clients.
So cyber-informed engineering builds on a lot of the cybersecurity principles that you've heard about today, but we turn the vantage point a little bit. We want to use the engineer in their conceptual design lifecycle and start thinking about cybersecurity there, leveraging the engineer's ability to potentially engineer out some of the cyber consequences that their system might face, potentially before they even choose what digital technology they will use to implement those functions or what digital technology they will use to secure them. I came to think about cyber-informed engineering first through Mike Asante, but I'll leave Mike Asante stories for others. And I'm going to tell you a Bob Anderson story. Bob Anderson is a control systems engineer who spent most of his career at the Idaho National Laboratory implementing reactors, and other people brought them to failure, but Bob made sure that the data that resulted from that testing was valuable and helped inform safety protocols that we use in commercial reactors today. So Bob really understands control systems and how to create them and how to make them perfectly responsive to the environment and the requirements of the system that he's working on. So we pulled Bob off of the site as we began our cybersecurity practice at the Idaho National Laboratory. And we had him set up a control system that, okay, and you all know the punchline here, we were then going to have cybersecurity researchers assess. So Bob did what Bob was trained to do. He set up that control system, he configured it, he put the safety protections in place that he understood how to put, and he turned it over to the cybersecurity researchers. Well, they did what they do. They came back and they shared the findings with him at the final report out for the vendor. And Bob was proud of what the cybersecurity researchers were able to find. There were some critical vulnerabilities, but mostly Bob was mad. Bob was a professional engineer, trained, who had spent his whole career depending upon the structures that he was taught to create safe and reliable control systems. And here was a gaggle of researchers who could turn all of that upside down. Bob was furious. Why didn't my education prepare me for thinking that this was possible? Why didn't my education prepare me to start asking questions to assess this risk? Because as an engineer, Bob's responsible for all risk with this system. And so as a result of that, Bob, and because I was in a cube next to Bob, me, resolved to ensure that universities started teaching erstwhile engineers about potential risks from digital systems as they begin their engineering degrees. So that just like they assess concrete or steel or any other materials that they build with, they can assess risk from digital systems.
So Ginger, I have a question for you. When you say the word engineer, what type of discipline are you referring to?
So I grew up in a family. My dad was an engineer. My brother is an engineer. And my dad was a double E, and he thought that double E was the height of engineering. Maybe it is. My brother is a mechie, so that's a little bit lower on the scale. But for my dad, an engineer was someone who graduated from a formal education program with engineering as the major course of study, and preferentially someone who then topped that off with pursuing a professional engineering license.
Thank you. So that's really helpful to have that context. So I am a trained civil engineer. I have a PE license. Most of the people who design and operate and who are really licensed and responsible for providing safe drinking water or collecting wastewater and treating it safely, they're civil engineers. Now, how many civil engineering programs over the last 30 to 40 years had any cybersecurity in them? How many licensure exams? The donut, there are 0. So what I've found is that when we go and we talk about cyber-informed engineering, all of a sudden the engineers, they start to listen a little bit because we're taking cyber, which is something they don't know much about traditionally, and engineering, which they do all day, every day. So I was speaking with a very large sanitary district about this a couple of weeks ago. And about 3/4 through the discussion, one of the engineers goes, "Oh, wow, we need this." So what we're seeing is almost a latent need that they understand they haven't been doing things right for a long time, but almost kind of like a young child, and I don't mean that as a pejorative at all. They're learning to communicate. They're learning from the people around them. And finally, we have a framework that we can use to enhance that discussion and hopefully get better.
So in the traditional engineering life cycle, and again, SANS is often an opportunity for instruction, so I'll take this opportunity. What I'm showing you is the V model of systems engineering, where the V corresponds that at each stage of a systems life cycle, we gather more detail, and the things that are across from each other on the V, the right side of the V validates everything on the left side of the V. And so as you progress through the V, you should be arriving at a system design that you start with the concept development and go all the way through until you end up testing and validating and transitioning the thing that you had the concept for. In our traditional cybersecurity validation process, we really put off thinking about cybersecurity risk until we're in the latter half of that V. With cyber-informed engineering, what we want to do is introduce cyber thinking upfront. But again, while we're still in our engineering development, while our requirements are still just a little bit fluid, while we still have the capacity to make changes in a system, and while we haven't accepted so much risk that we're overwhelmed by the risk we've accepted and we can't maneuver around it. So in this process, we start thinking about cybersecurity at the very beginning. Before we even have a system, we are thinking about what are the critical consequences? How will we secure this? What are the things that we need to defend? And we'll talk to you a little bit more about that as this talk goes on.
So very recently, West Yost was acting as an owner's agent for a greenfield water treatment plant out in the western part of the United States. And as an owner's agent, we had responsibility to review all of the engineering decisions, design drawings, et cetera. And so we got a deliverable from the design engineer. And this is a very large firm. They do all these types of designs on a regular basis. So they handed it to us and we said, you guys excluded the local hand-off auto switches on all of the control panels. And we said, well, that doesn't seem like a great idea. They said, oh, no, don't worry about it. And then we said, okay, well, what if this plant is under sustained cyber attack? They said, oh, that'll never happen. And we said, okay, so we have a fundamental disagreement in how this system needs to be engineered. But as the owner's agent, we were able to dictate to them that they had to include this little switch out at each control panel. And the more operators I talk to, the more instances I have heard of engineers trying to get rid of this because they're willing to just go all in on automation and remove all of those manual backups that have served the industry and many industries so well for so long.
So today, there are 12 principles within cyber-informed engineering, and we have only 30 minutes, and I'm not going to take you through all of them because I want to see the blinking light demo just as much as you do. So we bolded a few of them that we're going to talk about today, and I reference this as the temporary structure because cyber-informed engineering is still being formed. And I'll talk about what we're doing in the formation process at the very end, but I'll start by welcoming your participation before you even fully know what this is. So as you hear about these principles, if you like them, let us know. If you disagree with some of them or have a different slant on it, we want to know that too, because ultimately, this will be the package of ideas that we give all of the young engineers graduating.
So I was at a conference a couple of weeks ago, much like this, about this number of people, but it was all water sector people. And I said, I was thinking about cybersecurity culture, and kind of like what the previous presenters emphasized, is that we kind of have to become defenders of our infrastructure. And so I said, hey, who here considers themselves to be a defender of their organization and their system? One lady in the front slowly raised her hand. So what that meant is that I could give that group a very hard time for that little bit of time I was on stage, but it also really demonstrated that we need to have a little bit of a mindset change. And I think that I got some feedback from people who had never really heard that argument before, and that's important, right? They had never heard it before, and it started to change their mind a little bit. With all of the various advisories and everything that have come out since last December, it was sort of a little bit of a turning point for our sector. Right? We are defenders, and we need to adopt that mindset to really move forward with this and other ideas.
So I'll start with something that this is not the first time it's been said during this conference, and I'll say I'm really glad to hear that. And that is consequence-focused design. As we start out in the conceptual design phase, when we are still drawing things on paper and maybe cocktail napkins, this is the time for us to get a group of people, including our engineers and our cybersecurity experts, hopefully together, and talk about what are the potential consequences and the impacts that this system could have on the process that it's involved in, on the business that serves, and on the environment that surrounds it. And then as you come up with consequences, this is often a brainstorming exercise. We have to prioritize them. What are the most impactful of those consequences? And our CCE process calls those high consequence events. And what other ones are important for us to consider in our design, but may not be the thing that is most important for us to defend, at least at first. Things that we think about in terms of these consequences or disaster scenarios are the area of impact if this consequence occurred. What would that be? What size of the attack or what size of an impact could that make? What breadth do we expect this consequence to live within? Is this a brief outage that we think we could remediate, or that we'd like to ensure that we could remediate quickly? Or is this something that, if we design the way that we're thinking about, could have the potential to keep us out of operations for a long time? What would be the cost of these consequences in our system maintenance process? What would be the duration? How would they affect our long-term system integrity? In other words, could we easily remediate and say, oh, we reapplied the gold disk, we're fine? Or is the remediation something where we would have to restore a physical device that may have a long order time or may be very difficult to source? And finally, and most importantly, what are the impacts on safety of this consequence, and how should my system be designed to prevent that?
So one of the things within the last probably 2 years that I'm most proud of is I was working with a very large water utility out west. And we had done what we call a day without SCADA exercise, which is exactly what it sounds like, a tabletop exercise where we say, all right, you don't have automation. We design the scenario, and it's a really fun event. The people from the utility who participated in that were really taken aback by some of the things that they observed and that they heard. And what they asked us to do was actually write a preamble to their engineering guidelines. So you have guidelines and drawings and specs. And what we wrote in those guidelines was, hey, we did this tabletop exercise. There's this idea called cyber-informed engineering. Every single design that you put out will, 1, accommodate manual operations, and 2, reduce the consequences of the cyber physical consequences of a cyber attack. So we were mandating that this be done for every single one of their capital designs, and they do a lot of that design work. So there are good ways to do it. Engineers, we need rules. That's part of our personalities. So if you give rules up front, they will stick with them.
The next thing we wanted to focus on, and I took this out of safety controls because at the National Laboratory, we focus, like many of you focus, very much on ensuring that the work we do is safe. And we use a philosophy incorporating a hierarchy of controls where if there is a potential hazard, we separate the human from the hazard in a variety of ways, hoping to choose the most practical and effective control for the hazard. In the safety consideration, the best thing we can do with a hazard is eliminate it. Well, the same is true with a potential cyber risk. And if there's a path towards elimination as we do our system design and we realize we are going to have a class or category of cyber risk, what could we do within our design to potentially eliminate it? Okay, that may not be possible. So our next option is, can I take maybe a function that leads me to that risk? And can I separate that function or capability with something else that doesn't have quite the same risk? At the lab, we have people doing radioactive testing. They test whether they could actually find radioactive material. And we don't actually scatter radioactive material out on our site, but we use a simulant that responds to a Geiger counter. And so it gives them the look and the feel of a real situation, but substituted so that they're not exposed to the hazard. In a cyber situation, maybe I can get rid of a certain class of input port or a certain method of doing something if that potentially adds risk to my system. I can use engineering controls where I find a way to separate the system from that hazard. So there is no way that a user or authorized or unauthorized could access that potential risk. And then we get into the lower part of the pyramid. And the interesting thing of the hierarchy of controls is the easiest things are on the bottom, and they're also the cheapest, but they're also the least effective. So we can make administrative controls, but of course, adversaries are unlikely to read our lab-wide procedures or our manuals of operation and abide by them. So that might not work very effectively for us. And of course, personal protective equipment, if we've issued maybe virus scanners or something that helps mitigate a risk that might enter our system, our adversaries are also not going to have access to those. So we want to teach these engineers to use that safety mindset that they get and apply it to cyber situations, just like the way we've been thinking about it here.
So a few years ago, I was doing a site walk as part of an all hazards risk assessment. So cyber was a small component of it. And these are the best things, right? Because I get to go and walk the plant and listen to all the stories that all the operators have. And we were standing right by the giant pipeline that brings raw water into this water treatment plant. And the operator says, "Hey, look at this." And I kind of go over there and it's like, there's this little sort of line of corrosion, in the bracket. And I'm like, okay, well, what's that? And he said, "Oh, when we were getting this plant started up, there was a programming error in the PLC that controls the automated valve, influent valve. It closed too fast and it created something that we call water hammer. It's like a pressure wave that goes up and down the pipe until it dissipates. But the water hammer event for this was so large that this pipeline bounced a couple inches over." Now, when I said, "Oh, did you just change the gearing on the gearbox?" Because I'm thinking about this from a cyber physical perspective. They said, "No, our integrator fixed it in this PLC program." I said, "Well, but you're still going to fix the gearing." And they're like, "Yeah, that's a really good idea." I don't know if it's been done, but hopefully I'll get to work with them again in a few years because they get to do it every 5. And I'll ask that same question.
The next thing we wanted to talk about is design simplification. Today in the OT world, just like everywhere else, features are rampant. And it's easy for teams to get excited about all the things that they can put into a system and all the ways that it can help them. And of course, the vendors also create systems with many more features than an asset owner may need. So part of a good system design is reducing the system to the necessary functions that you can reduce it to. However, with the caution, we cannot remove resiliency. And so we have to reduce it to simplify it and then do a resiliency check and just make sure that we've got enough of the system that will fulfill our requirements, provide some resiliency, but not provide undesired features that our adversary may take advantage of.
So who here wants to be smart? I do, right? All right, thank you. So there's a huge buzzword in the industry to be a smart utility or a smart city. And as Ginger just mentioned, that means there's going to be all kinds of features and apps and data and everything else. Most organizations simply aren't ready to take on that. They also don't know that they need to turn all of those things off. So it's really an important element here to ask the vendors, like, hey, turn off everything other than what we're using. That hopefully will be something that people understand a lot better within a few years.
Just with a caution, and this is where the benefit of having a cyber person come in, off to the asset owner and the engineer may not mean off for the adversary. And this is a great point to have engineers and cyber people talk about what does it mean to truly disable a function so that it's not available for someone living off the land.
Great point.
Go ahead. Engineering information control is how we control the information that we put out about a system design or a capacity that we are building. At the Idaho National Laboratory, we, just like many of you, when we are assessing a system, we start with an open source search. And it is absolutely staggering how many times we can find on the internet drawings that give us blueprint-like vision of where system components are, model numbers, version numbers of installed software, because the vendors who put these installations in are very proud of them. And the contract specifications that are exchanged as a part of the procurement process require specificity. And as an adversary, when that information is available on the internet, that is free parking for me. In addition, job listings are a wonderful place for me to start to understand what are these people hiring, because that influences what they're probably using. A lot of these sources of information don't come directly from the engineers creating the system, but they are within the support process, because a lot of the people who are supporting the engineers may not have the conversation about what information is important to protect, who should have that information, and how it should be protected. Oh, and for how long? Because people think, oh, we've issued the contract, so now we can let the documentation out, right? We're only going to have the system for 30 years, so it's fine. We can just let that go. So all of this comes into thinking about how do we control the information about the engineering projects that we create.
So in the water sector, most of the organizations that own the assets are public entities. So they're always caught in this balance of having pretty draconian, public procurement rules, wanting to demonstrate to their ratepayers that they as a public agency are doing a good job. And what this results in is the publication of what we call water system master plans or wastewater system master plans. And if you look at those, a lot of them have an enormous amount of detail about where assets are, what the assets do. And from if you're a learned person when it comes to these sorts of systems, you can pretty much deduce what's really important and what's not. Now, I do say, that's sort of alarming, but at the same time, I think coming really from our IT colleagues, they have really started to ratchet down the procurement information that's put out when it comes to the control system. So instead of giving a specific PLC model, they'll just say PLC, and then you have to go and actually talk to the utility to figure out what they're looking for if you want to propose on the project.
I really do love this diagram. I pulled it from an over 20-year-old paper that was written in 2001 by Steve Rinaldi about interdependency evaluation. And it's an eye chart for those of you in the room. So I invite you later, either Google Rinaldi and his paper or look at this more closely. But as we're building systems, nothing happens in isolation. And as our last speakers talked about, engineering especially does not happen in isolation. My system depends upon inputs from other systems and processes to function, and it produces outputs that other things depend upon. And so it's important early in that system design to start thinking about those interdependencies and where particularly there may be frailties that I will experience from a digital consequence to an entirely other system that then could affect me. And so I not only have to protect my own system from those impacts, but I also have to be aware of how they could come to me from somewhere else.
So for those of you that have a little bit older eyes, at about 2:30, there's a spoke on this wheel that says state of operation. And even smaller print, there's a little sub-spoke that says stressed or disrupted. So within the US, the water infrastructure has an aggregate grade of C- from the American Society of Civil Engineers. That's the quality of the infrastructure that unfortunately we have. Now, one thing that's really good is that's up from the D's recently because investment has increased. We've recognized that we really need to do a lot more rehab and renewal on these physical assets. So remember that big pipeline that I mentioned that bounced a couple of inches? What if that pipeline was, say, 70 years old? It was built with post-war steel. Do you think it would have survived that water hammer event? Gets a little touchy. Water utilities are starting to worry about those sorts of things. Now, also, it's water. What if that was a wastewater pipeline that was old, that had water hammer go through it? What do we call that, Ginger?
I call that a poop hammer.
Let's see what our artist extraordinaire can do with that.
And the final thing we wanted to highlight out of our 12 principles is active defense. You know when the best time is to think about how you're going to defend a system? It's when you're creating it. It is when, again, you're in this conceptual design process. All things are possible. You're going to have to accept a lot of risk in the process, but understanding what you have as far as defensive assets will make you far better in understanding exactly how to design that system going forward. So with active defense, we're thinking about how we're going to defend the system, what tools, capabilities, especially what people we have, and how we might bring the right groups together to understand what's actually happening, so that we don't end up with the cyber team on one side scratching their heads and the process team on the other side, both convinced that the answer is something completely different. And then we have to walk that diagnostic process.
So when we think of active defense, oftentimes the first thing that comes to mind is, some fancy OT monitoring solutions. But really, our operators have been doing an excellent job of monitoring their processes and actively defending them against accidental and intentional mishaps for over 100 years. So one of the operators that I've had the opportunity to work with started his career in the 80s. And his mentor, and this may have been just to shock my friend when he was young, they were at a wastewater plant, and he said, okay, well, we're going to walk the plant and we're going to monitor the system for general health. And there's biological systems in there. And so this senior operator went over to the sludge bed and he grabbed some sludge, wastewater sludge. Yes, it is what you think it is. And he kind of felt it in his fingers for grit and viscosity, gave it a little sniff and said, yeah, we're doing okay today. Now they had to do some chemistry to back that up. But our operators are really talented when it comes to those sorts of things. They walk out on the plant floor and something doesn't look right, smell right, sound right. They know that just intuitively after their years and years of experience.
Thank you for giving me a new visual for what hands-on defense looks like.
There you go, Ginger.
So the Idaho National Laboratory, we have spent a lot of time developing cyber-informed engineering and expressing it through a product that many of you have heard about called consequence-driven cyber-informed engineering. And that is indeed a methodology that we use today to start highlighting those high consequence events that a system could have in either existing systems or systems that are being designed, identify the systems that are connected to those high consequence events, and then how we might mitigate those potential events, either through the intervention of engineering solutions or cybersecurity solutions. But there's more. With cyber-informed engineering, the Idaho National Laboratory and the Department of Energy was tasked in the 2020 National Defense Authorization Act to create a national strategy for cyber-informed engineering. We have created that with 5 distinct pillars: awareness, education, development, current infrastructure, and future infrastructure. And in the next couple of weeks, we'll have a sign-off from the Secretary of Energy for that strategy. And so that's good. That's step 1. But step 2 is where all of you come in. Once that strategy is signed, we would like to start implementing those pillars of cyber-informed engineering. First, by having some engineering schools, and we have a few that have volunteered, stand up and start building this into their engineering curriculum. Second, start developing the tools, the charts, whatever an engineer might need to develop the best questions that they can start asking in system design of all of their cyber counterparts, so that they can start trading off risks, because that's what engineers do. And then third, to develop methods and extend methods, including CCE, but not limited to that, of applying this both to infrastructure that currently exists and to the infrastructure someone just drew a pressure vessel on a cocktail napkin somewhere, and whatever that infrastructure is going to be in the future, I want to make sure that we've used cyber-informed engineering to make it safe.
So as the penultimate presentation here this week, I want to go back to Chris Inglis's presentation yesterday, and he said some things that were really important. One is we want to be resilient by design. My opinion, and I think Ginger's as well, is that CIE is how we get to be resilient by design relative to cyber. And there's all sorts of other all hazards benefits that come from this. So the other thing you mentioned was the Infrastructure Act. So there's going to be all kinds of money coming down from the federal government. The water utilities and wastewater utilities are really getting ready to make some substantial upgrades to their infrastructure. One of the things that does happen in our industry sometimes, though, is that there will be a design that's done. It'll get to 90%, something will change, GM will leave, and that project will get put on the shelf. Now, that shelf, it may have been on that shelf for 10 years or so. Now, we have to take that design before it gets implemented, get out the CIE lens and look at that project and make design changes before it's implemented. So one of the things that I've heard from Ginger and some of her colleagues is that the long-term goal is that if you're an engineer or an asset owner and you implement a system or an asset that is not designed using cyber-informed engineering, you will be negligent in your job. When I say that to a licensed engineer, they literally stand up straight. That's the type of reaction we need to get. So I hope that you found this helpful today. And with that, Ginger?
I'll say, in addition to the Slack channel, which I will monitor and respond to later tonight, if you're interested in taking part in any of the working groups, please email, and it's an easy email, CIE@inl.gov.
And you can see my email up there, a little bit more complicated than CIE.inl.gov, but I'm also on LinkedIn. Thank you all very much.
Thank you.